And so we're glad to have today Marcus Mazari-Armida, who will be talking about model-theoretic stability and superstability in classes of modules. So you can start when you're ready, Marcus.
Okay, first of all, thank you for the invitation and for the introduction. Yes, as it was just mentioned, the title of my talk is Model-theoretic stability and superstability in classes of modules. So before I begin, I'll give some background. So abstract elementary classes were introduced by Sherlock in the 80s, and they were introduced to study infinitary model theory. The theory of abstract elementary classes has developed rapidly since then. So there's probably more than 3,000 or 4,000 pages on AECS, but very few applications have been found, or like very few, let's say applications, or there's very few examples. In particularly for people like working on like model theory, common topic is every time you submit a paper about AECs, they ask you if there's any example, like any new example that's not first order. So because of this, at some point, I decided to start looking at examples and applications. First, I started looking at abelian groups. And then I realized that, okay, modules aren't that different. And actually, you have the extra degree of freedom that you get from changing the ring. So then I said, okay, let's look at AECs of abelian groups and modules. And yeah, I want to point out that I wasn't the first one to look at this kind of examples. In particular, there's a paper by Baldwin, Eklof, and Trilfach on like AECs of modules. But I think I was the first one to do it like systematically. And when I say like I want to study AECs of modules and abelian groups, for this talk, this means that we're going to look at stability and superstability. So stability and superstability are two of the best understood dividing lines. This was first introduced by Sherlock for first order theories. And then after that, they were extended to AECs also by Sherlock like in the 90s. And they seem to be like if a class is stable, it seems to be very nice. And if it's unstable, it's very hard to analyze in some sense. So this is the background. Now let me tell you the outline a little bit. So the talk will be divided in 4 parts. First, I'm going to talk some basic notions about AECs. Then I'm going to talk about stability, universal models, and then I'll finish with superstability. When I was preparing the talk, I realized that like each one of 2, 3, and 4 could be a talk by itself because there's like a lot of material, and I was like actually thinking of just talking about stability, but then I realized that it's probably, what I wanted to do with the talk is to give you like a feeling of the subject of AECs of modules. And I thought this could be achieved in a better way by telling you a little bit about each one of them instead of just like giving you like a lot of details in one specific topic. So that's what I decided to do. So let's talk about first the basic notions. So first, I have this slide because I'm not sure of the background of everyone like listening to the talk. So we have like given a ring R, we have the language of the ring of modules. We have 0 plus minus, and we have a unary function for every R in R. And we're going to be interested in positive perimeter formulas. So phi is a positive perimeter formula if it is an existentially quantified finite system of linear equations. And then we're going to be interested in PP types. So the PP type of B bar over A in N are all the PP formulas satisfied by B bar in N with parameters in A. So from a first order theory perspective, the reason we care about PP formulas is because for complete theories, we have PP quantifier elimination. But actually, the reason we're interested in PP formulas is because of the relation of pure submodule. So let me remind you what a pure submodule is. So M is a pure submodule of N if and only if first you have to be a submodule. And the important property is this one here. So the PP type of A bar over the empty set in M is the same as the PP type of A bar over the empty set in N for every finite tuple in M. So from a model theory perspective, this is a weakening of elementary substructure. From a module theoretic perspective, this is a weakening of being a direct summand. So if you're a direct summand, you're a pure submodule, but you can be a pure submodule and not a direct summand. Okay, so this notion, although it, by the way I introduce it, it looks like a very, I don't know, logic, like model theoretic notion. It was actually first considered for by algebraists. So it was introduced in the 20s for abelian groups, and then in the 50s it was introduced for modules in general. And the more algebraic characterization is the fact I have down here, which says that M is a pure submodule of N if and only if for every L right R module, the map from the tensor product from L and M to the tensor product of L and N is a monomorphism. So this is, I mean, I'm going to say a little bit, I'm going to use some other stuff about module theory, but this is like the basic stuff, I would say. So let's go to AECs. So again, I saw that there have been some talks about AEC, so I'm just going to go, I'm going to give the definition very briefly, and then we'll go on. So an abstract elementary class is a pair, K less or equal to K, where K is a class of structures, and less or equal to K is a partial order. The actual definition has like 6 axioms, but I would say that the 2 key axioms are the ones that I have here. So one is the Tarski-Bott axiom, which basically tells you that you're close on the directed colimits. And the other axiom is the Lovenheim-Skolem-Tarski axiom, which tells you that given any model M and a subset of M, you can find a small subset in the class containing A. For those of you more familiar with category theory, which I think most of you are more familiar with category theory, AECs are close to concrete accessible categories, close on the directed colimits, where all morphisms are monomorphisms. And I have concrete in quotations because you need like some extra hypotheses. But for this talk, actually, we're gonna just talk about AECs of modules. So what do I mean by AEC of modules? I mean a pair K. Here, the order, it's always pure submodules. This has to be an AEC, and K has to be contained in R mod for R an associative ring with unity. So this is a restrictive definition for AECs of modules, in particular because of this thing here. So I'm just gonna talk about AECs of modules with respect to pure embeddings, but in principle, you could talk about AECs of modules with respect to embeddings or elementary embeddings or RD embeddings, and then things would change. But for now, and for all this talk, every time I say, okay, I'm gonna look at R modules, I mean R modules with pure embeddings, or absolutely pure modules also with pure embeddings, and like that. Yeah, and it will be like that for the whole talk. Okay. So now let me introduce a few basic definitions. So we have the amalgamation property. So the amalgamation property tells you that you have the amalgamation property if for every span, so if M is K substructure of N1 and N2, this can be completed to a commutative square. And although this seems like a very, it's a very easy property to understand, it's actually, it's not trivial to prove that something has the amalgamation property or not. So examples of classes that have the amalgamation property, okay, clearly our modules has it. And this just follows from the fact because it has pushouts. So every class that has pushouts has the amalgamation property, but it's not true that every class that has the amalgamation property has pushouts. Another example, which is like less well known, local injective R modules also have the amalgamation property. So what do I mean by local injective R modules? M is local injective if given any finite tuple in M, you can find an injective submodule that contains the tuple. Okay, and this class, for example, has the amalgamation property but doesn't have pushouts. Another example, now an example that doesn't have the amalgamation property is the class of a left-one free abelian groups. So left-one free abelian groups are those groups such that every countable subgroup is free. And actually, to prove that something doesn't have the amalgamation property seems to be way more complicated than to prove that it has it. So for example, to prove this result, the only way I know how to prove that it doesn't have the amalgamation property is use some result by Schellach that says that there's no universal model. And since this class will be stable, then it doesn't have the amalgamation property. But there's no direct way of actually proving it. There's no like theorem that says, okay, if you have this property, you cannot have the amalgamation property. And then there's other classes, which we still don't know if they have the amalgamation property or not. And an example of this is finitely Butler groups. I won't give you the definition. I just want to tell you that even for like classes of abelian groups, which should be easy to like say if it has the amalgamation property or not, there are still many classes we don't know anything about them, even with respect like these easy properties. Okay, then okay. Now there's other two properties that an AEC might have or might not have that will be interesting for us. One of them is the joint embedding property that basically tells you that given any two models, you can embed it into a bigger model. And the other one is non-maximal models, which tells you that for every model M can be properly extended. Again, these properties might fail for classes of modules, but at least in this talk, all the classes we'll talk about, they are close on the direct sums. And once you're close on the direct sums, it's easy to see that you have the joint embedding property and you have non-maximal models. Any questions so far about like these three properties? So this was the basic notion. So now let me talk about, okay, so now we're gonna talk about stability. So as I said at the beginning, so stability was introduced by Shalach in '69 for first order theories. And then this was extended in the '90s for AECs. And it seems to be for a while, like for, I guess like for around 20 years for first order theories, it seemed to be that if you were stable, you could do some model theory. And if you were unstable, you couldn't do anything. Now we know that if you're unstable, you still can do some stuff, but the line, like being stable seems to be like a very important property to have. Okay. So before I introduce, okay, so let me introduce Galois-types first, and then I'll introduce stability. So Galois-types are a semantic version of first order types. So for simplicity, I'm gonna assume the amalgamation property. So what are Galois-types? So first we have the triples. We have K3, which is the set of triples A, M, N, such that M is a K substructure of N and A is in N. And then we define a relation in K3. And then we say that two triples, so A1, M1, and 1 is related to A2, M2, and 2. If and only if. So first we have that M is equal to M1 equal to M2. And then the important thing is that you have two maps, FL from NL to N, which fix M. And so you can amalgamate them, but more importantly, and this is where the A1 comes in, A1 is mapped to A2. Okay, one can see that this relation E is an equivalence relation. To prove that it's transitive, you need amalgamation. And then once you know this is an equivalence relation, we can define the notion of a Galois type. And then we say that the Galois type of A over M in N is just the equivalence class of the triple AMN. And for us, it will be very important, not only the notion of Galois type, but the collection of all types. So GS of M is the set of all Galois types over M. Okay, so now let's introduce the notion of stability. So we say that K is lambda stable if the number of types over M is less or equal to lambda for every element M in K of cardinality lambda. And then we say that K is stable if there's a lambda such that K is lambda stable. Okay, so like a very well-known theorem from first order model theory is the next theorem due to Fisher and Bauer. They showed in the 70s that if T is a complete first order theory extending the theory of modules, then the models of T with pure embeddings is stable. So if you had seen this result before, it's weird that I have pure embeddings here, but the reason you can have pure embeddings here and the result still holds is because we have PP quantifier elimination for complete first order theories. So this result in some sense was, so this is not just our result, but in some sense, first order theories of modules are like the canonical example of stable theories. So, and then after this, this was proved in the 70s. And then like in the last few years, people have proven that some AECs have like this property too. So like, for example, Baldwin, Eklof, and Trilkvax show that the torsion-free groups with pure embeddings are stable. Then, Shalach proved that reduced torsion-free groups are also stable. Then I proved that torsion-free groups are stable. Then Lieberman, Rosicky, and Basie proved that flat modules are stable. So then after seeing all of these results, I thought, okay, maybe this result can actually be generalized to all AECs. So this is the question. So let R be an associative ring with unity. If K with pure embeddings is an AEC of modules, the question is K stable? Okay, this might be too much. So, okay, what about classes of abelian groups? So, and then, okay, maybe it's not even true for abelian groups, but I'm sure there has to be a kind of ring where this has to be true. So the question is this true in general? My hunch is that probably it's true, but not in general, but under some hypothesis, like at least being close on the direct sums, you probably can do something. And what I'll do for the next like couple of slides is give some positive results under some algebraic assumptions. So the question as it's written here is still like, I would say wide open, and you'll see like ways of approaching this problem in the next slides. So first, let's talk about stability under hypothesis 1. So hypothesis 1 is, okay, K is an AEC of modules. We assume that it's close on the direct sums and close on the direct summands. I see these two hypotheses as some like weak hypothesis. And the important hypothesis is the third one. So the third one tells you that K is closed under pure injective envelopes. So what do I mean by that? That means that if M is in K, then the pure injective envelope of M is also in K. If you have never seen pure injective envelopes, they're very similar to injective envelopes. You just change like submodule for pure submodule and injective for pure injective, and it's the same notion. Okay, so this might look like a, I don't know, random hypothesis. So let me give you some examples. Okay, the class of our modules satisfy it, but that's not an interesting example. More interesting example that we'll talk about a lot is absolutely pure modules. So let me remind you what that means. So M is an absolutely pure module if for every n, if M is a submodule, then M is a pure submodule. So examples of absolutely pure modules are injective modules, because if you're an injective module and you're a submodule of something, then you're a direct summon. So then you're a pure submodule. So this is one kind of example. And actually, you can characterize Noetherian rings by saying every absolutely pure module is actually injective. We'll talk about that later. Other kind of example, I already talked about this one, so locally injective modules, and then there's an extension of that for locally pure injective modules. From a model theory perspective, this example are interesting because they are not first order axiomatizable. So we're doing something new, something that couldn't be done by like the methods known in the 70s and 80s. All right. So let's see how stability works in these classes. So in these classes, what one can do is the following. So we have this lemma, which tells you basically, so you take M, N1 and N2 in K. M is a pure substructure of N1 and N2, and you have a tuple in N1 and a tuple in N2. Then what you can show is that if the Galois types in the class are equal, then the PP types are equal. So regarding this result, this direction is always true. So if Galois types are equal, PP types are equal. And this is just true because you have that embeddings are pure embeddings, so they preserve PP formulas. So there's nothing to do in that direction. So it's an easy direction. And the hard direction is the other one. Like if PP types are equal, then Galois types are equal. And then for this direction is where I use the fact that you're close on the pure injective envelopes first, and then you're also close on the direct summons. So this is where like the third hypothesis come in. Now, once you have that PP types are the same as Galois types, then you can prove stability, and then the proof is not that hard. So this is the result. So let lambda bigger than equal than LSK. If lambda to the R plus LF0 is equal to lambda, then K is lambda stable. So let me give you like small sketch of how the proof works. So what you do first is, okay, you take an enumeration of GS of M. So we have an enumeration of the Galois type of AI over M in N, such that I is less than alpha. Here it's important that we realize everything in one model, but because these classes have the amalgamation property, that's fine. And then what you do is you transfer your problem about counting types in the AEC to counting types in first order theory, in a first order theory. So what you do is you send the Galois type of AI over M in N to the PP type of AI over M in N, and then using the fact that if the PP types are equal, the Galois types are equal, you have that phi is injective. And then using the fact that you're in a first order theory, it's easy to show a stability. So this follows from like Fisher and Bauer result. So what you should take from this is, okay, if you can prove that Galois types are PP types, then basically you transfer everything to first order and then it works out. But I have found examples where I cannot do this. And I think there are examples where Galois types are not PP types, but you're still stable. So this makes the problem more interesting. If you would always be able to identify Galois types with PP types, then the problem wouldn't be that complicated. I mean, the result, I think it would be interesting, but it wouldn't be that interesting because the method wouldn't be like so surprising. So let's look at another hypothesis. So now let's look at stability under the second hypothesis. So the second hypothesis is similar at the beginning. So K has to be close on the direct sums. K has to be close on their pure submodules. So here we strengthen from being close on the direct sums to being close on their pure submodules. And then finally, again, the key property is this third one. So what I assume is that K is close on their pure epimorphic images. So let me just remind you what it means to be a pure epimorphism. So F is a pure epimorphism if it's an epimorphism. And then the important thing is that the kernel of F is a pure submodule of the domain of F. Again, this might seem like, okay, these are some hypotheses. Are there any examples? Yes, there are some examples. So, okay, our modules satisfy it. That's not that interesting. Then flat modules satisfy it. And this is probably like the reason I started looking at this type of classes. And then other classes that satisfy it as well are abelian P groups. This we'll talk about abelian P groups later on. Let me just remind you of the definition. So an abelian P group, G is an abelian P group if every element different from 0 has ordered P to the m. And also we have this class of injective torsion modules. I don't want to give the definition. They are just like a generalization, like the natural generalization of torsion abelian groups for any ring. Okay. Are there any questions so far? Okay. Something that I would say that's important to say is that, okay, flat modules satisfy hypothesis 2, but they don't satisfy hypothesis 1. So like hypothesis 1 is not containing hypothesis 2. And the reason for this is because flat modules aren't closed in their pure injective envelopes. And this is like well known in some sense. On the other hand, there's also classes that satisfy hypothesis 1 and they don't satisfy hypothesis 2. And an example of that is, for example, absolutely pure modules. They are not closed on their pure epimorphic images. So there are disjoint class. I mean, there's no intersection because you have R modules and every first order, every definable class satisfies both hypotheses, but they're not the same. Okay. So in this case, the question is, are Galois types the same as PP types? So my answer is, I still don't know. But what I know is that, at least in the class of P groups, you can identify Galois types and PP types. But there's a reason you can do it for P groups. And for example, the main question for this class is, can you do it for flat modules? Can you identify Galois types and PP types for flat modules? And I tried to do this for a long time and I didn't get anywhere, so I don't know. And so to prove a stability in this case, we need a completely different strategy. So that strategy requires this result. So if we assume that K is closed on their pure submodules, direct sums, and isomorphisms, what one can show is that K is closed on their pure epimorphic images, if and only if K is closed on their pushouts of pure embeddings in the category of our modules. What do I mean by closed on their pushouts of pure embeddings? I mean, if you take two pure embeddings F1 from N to N1 and another pure embedding from M2 to N2, then if P is the pushout of F1 and F2 in R mod, then the pushout is actually in K. So, okay. So this is the key result to get a stability, actually, like this equivalence between these two. Okay, so let's see. So how do I get a stability? So for this class, it's actually significantly more complicated than under hypothesis 1. So what I was able to do is, first you have to define a non-forking relation in Galois types. So non-forking relation for AECs were introduced by Schellach in the, I don't know, like 10 or 15 years ago. And then more recently, Lieberman, Rosicki, and Basie introduced non-forking relation for categories in general. The definition is actually very long, and it would take me probably like 30 minutes to give like all the definition. So what I decided to do is, instead of giving you the definition, I'm just going to tell you the two properties that I care about, and that those two properties are enough to actually get a stability. So the first one is uniqueness. So uniqueness tells you, like, if M is a pure submodule of N, P and Q are two types over N, P and Q do not fork over M, and the restrictions over M are the same, then the types are actually the same. And then the other property that's very important to prove stability is local character. And local character tells you that if P is a type over M, then there has to be some submodule of M such that P doesn't fork over N. And the important part here is that N has to be small. Okay. So I won't tell you how to prove these two results, but what I'm going to tell you is what exactly is non-forking in this case. What do I mean by non-forking? Once you know what you mean by non-forking, the results, I mean, you still have to do some work, but I think the hardest part is to think of a non-forking relation for modules. And then proving that it works, it's slightly easier, I would say. So what do I mean here? So the Galois type of A over M in N doesn't fork over M0. The idea, there has to be some models, M1, M2, and N prime, such that first A is in M1, then the model M, so the original model is contained in M2, N is contained in N prime, then, and the most important part is this relation here. So M1 is free from M2 over M0 in N prime, but what does it mean to be free? So M1 is free from M2 over M0 in M prime if this holds. So if P is the push out of the inclusion from M0 to M1 and the map from the inclusion from M0 to M2 in R mod, then the unique map P from the unique map T from P to M prime has to be a pure embedding. So this is the relation. So the relation basically is, okay, so there's some very long definition, but what you should, the important information from this slide, I would say, is this part here. So you can define some like relation of freeness, and the relation of freeness is exactly this thing here, which is like if you take the push out of the arrow from here to here and the arrow from here to here, then because you have the push out, there's a unique map from P to N prime, and then this unique map has to be a pure embedding. So this relation was introduced by Lieberman, Rosicky, and Basie under some extra hypothesis. And what I was able to show is that under hypothesis 2, this relationship is nice enough. And in some sense, I think hypothesis 2 is necessary. And the reason for that is because you kind of need this thing here. You need to be close on their pushouts in K, because if not, you cannot prove existence. And if you cannot prove existence, a notion of freeness without existence is a very weak notion. Okay, so yeah, so okay, and then you have to prove these two things, and I won't prove them, so it would take a while to prove them. Okay. And now, once you have uniqueness and local character, it's a general result that you can prove stability. So again, we have the exact same result as under hypothesis 1. If lambda to the size of R plus LF0 is equal to lambda, then K is lambda stable. And then again, the proof is not that complicated. At the beginning, I had it in my slides, but at the end, I decided not to write it down. Are there any questions about like hypothesis 2 on how to get a stability? Okay, so as you can see, it's completely different. So in hypothesis 1, we prove Galois-types are PP types, and then we use first order theories. In this case, we have to do a completely different construction, get a non-forking relation, and then from a non-forking relation, then we get a stability. Okay, so now, let's talk about one last example. So the question that I had, like question 1 was, is any AECS of module stable? And then what happens for abelian groups? So I think that for torsion-free abelian groups, I kind of have an answer, and the answer is yes, under some hypotheses. So the hypotheses are, so you take an AEC, K is contained in the class of torsion-free groups, K has arbitrarily large models, and K is closed under pure submodules. Then again, you might say, okay, this is a random hypothesis. So let me give you some examples. Torsion-free abelian groups obviously satisfy it. A left-one free abelian groups satisfy it, and finally Butler groups also satisfy it. Okay, so once you are close on their pure submodules and arbitrarily large modules, then you can get a stability very easily. So the result is, again, it's the exact same result. If lambda to the size of the ring plus LF0 equals lambda, then K is lambda stable. So how does the proof work in this case? So in this case, one can actually identify Galois types with PP types. And the proof in this case is different than under hypothesis 1, but this can be done. And once you know that Galois types are PP types, then the proof works the same way as under hypothesis 1. So basically, you transfer everything to first order, and then you have it. So then you might ask why it works for torsion-free abelian groups, and it doesn't work for torsion groups or for any, like for other classes of abelian groups or modules. And the reason is this thing here. For torsion-free abelian groups, if you take if N1 and N2 are pure submodules of N, and they are all torsion-free, then N1 intersection N2 has to be a pure subgroup of N. And this happens because if you have a divisibility condition for abelian groups, for torsion-free abelian groups, it has a unique solution. While if you look at torsion groups, it can have many solutions. So when you take the intersection, maybe the solution for one group and for the other group is not in the intersection. It's not in the intersection. So basically, that's the problem why it doesn't work for classes of torsion groups. And then what I realized is, okay, this result can be extended to the following thing. So if you assume that R is von Neumann regular, So what is it? Like a ring is von Neumann regular if embeddings are the same as pure embeddings. So under this hypothesis, if K is closed on their submodules and has arbitrary large models, then K is lambda stable for every lambda, such that, again, the same hypothesis, lambda to the size of the ring plus LF0 equals lambda. Again, the reason this proof works for like von Neumann regular rings is because if you take, because basically for von Neumann regular rings, you have this result. You have that if you take two pure submodules, intersection is a pure submodule. But this doesn't work for other rings. I don't know if there's, if you had a, okay, yeah. But I see this as a very weak result towards the actual question. So asking for the ring to be von Neumann regular, I think it's like a super strong result. Yeah, so super strong hypothesis, not result. Okay, so let's look at, okay, that's all I wanted to say about the stability. So, okay, so if you had never seen the notion of a stability before, I mean, seeing results about a stability, okay, you might think, okay, the results are nice, but for sure, it wouldn't convince me to try to solve the question, are AECs of modules stable, if you had never seen that notion before. So what I'm gonna do in the next section is to give like a algebraic reason why you should be interested in a stability. So for that, I'm gonna introduce universal models. So, okay, so let me begin by giving some notation because it will show up a lot. So K lambda is the set, are the models in K of cardinality lambda. And now we introduce, so we say that M in K is a universal model in K lambda. If M is in K lambda, and the important thing is that given any model in K lambda, there's a K embedding from N to M. What do I mean by a K embedding? So by a K embedding, I mean F is an isomorphism between N and F of N, and F of N is a K substructure of M. Okay, and then we say that K has a universal model of cardinality lambda if there's a universal model in K sub lambda. Okay, so let's begin with some examples. So let's look at, so if you take the cube vector spaces with the subspace relation, then for every lambda many direct copies of Q is a universal model of size lambda. So for a left knot, this is actually interesting because you have many non-isomorphic models, but the idea is every countable cube vector space has finite or countable dimensions, so then you can embed it to the vector space that has countable dimension. For lambda bigger than a left knot, you actually have categoricity, so being a universal model there, it's not much. Okay, so this is like some easy examples. So now let's look at a more interesting example for us. So let's look at the class of P groups with abelian, with the subgroup relation. So in this case, you actually also have a universal model for every cardinal lambda. And the universal model is the lambda many direct copies of the proof group. And the way you prove this result is, so giving any P group, you can embed it to a divisible P group. And then this group here is like the maximal divisible P group. And then this is the universal model there. Okay, so here we're looking at universal models with respect to the subgroup relation. So then what one can ask is, what happens if we change subgroup for pure subgroup? And this question is question number 2. This question appears in a book called Abelian Groups by Laszlo Fuchs. If you have never heard of this book, this is like the canonical reference for anything regarding infinite abelian groups. So it's a 700 pages book on abelian groups. And when you start looking at it, you realize that abelian groups are actually very, very complicated, and especially infinite ones. And you realize that set theory and infinite abelian groups are actually very connected. So the question that Fuchs asks is the following. So he asks basically what happens if we change subgroup for pure subgroup. So for which cardinals lambda does the class of P groups with pure embedding has a universal model of cardinality lambda? And then he also asks what happens for torsion-free abelian groups. What I'll do is I'll talk about, since I solved the question for P groups, I'm gonna talk about P groups. Shelach had actually already solved the question for torsion-free abelian groups before I started working on this. And there's 2 reasons why the classes are different. So from a model-theoretic perspective, P groups aren't first order axiomatizable. So that's a important difference, and torsion-free groups are first-order axiomatizable. But if you look at Shelach's proof, the big difference comes from the fact that in torsion-free groups, divisible conditions have one solution, and in P groups, they can have many solutions. So that's like actually the main difference, I would say. Now, before I show you how to solve this problem, let's just think a little bit why. So, okay, so the question with the subgroup relation was easy in some sense, like it was known for a long time. What happened? Why, if you change subgroups for pure subgroup, things just become more complicated? Or at least why this can't be the universal group? And the reason this cannot be the universal group with respect to pure embeddings is because if G is a pure subgroup of H and H is divisible, and you're a pure subgroup, then G has to be divisible. And then since this is a divisible module, that would mean that if this was the universal model with respect to pure embeddings, that would mean that every P group has to be divisible, and this is obviously not the case. So that's why this doesn't work. Okay, so let's talk about universal models in the class of P groups with pure embeddings. So first, okay, under GCH, there's not much to do. So under GCH, there's always a universal model for every uncountable cardinal. And in this case, what happens is that the class of P groups with pure embeddings is an AEC. It actually has the amalgamation property, joint embedding property, and non-maximal models. And then once you have these three properties, you can build like kind of saturated models, and then you're done. So the question is interesting. What happens if, I mean, can you prove anything without GCH? And this is the first result here. So if lambda to the left 0 equals lambda, or for every mu less than lambda, mu to the left 0 is less than lambda, then the class of P groups with pure embedding has a universal model of cardinality lambda. So how does the proof work? Where does the stability come in? So stability comes in this first step. So the first thing I showed is that if lambda to the left 0 equals lambda, then the class of P groups with pure embeddings is actually lambda stable. And actually, I already kind of proved this result because the class of P groups satisfies hypothesis 2. But actually for P groups, to be honest, you can do a way easier argument than the one I presented under hypothesis 2. Because for P groups, you can identify Galois-types with PP types. And once you have that, then you can transfer it to first order. Okay. So this is the first step, and this is the place where stability comes in. Then the next step is, okay, the class of P groups with pure embedding has AP, JEP, and non-maximal models. And in this case, it's actually quite easy. And because why? Because P groups have pushouts, so they have the amalgamation property. And P groups also are close on the direct sums, so then have joint embedding property and non-maximal models. And then once you have the stability and these three properties, then using this result here, which is a result due to Kusera and myself, then you can have P groups. Then you have the P groups with pure embedding has a universal model of cardinality lambda if it either satisfies this hypothesis, or either you're stable or you are like confinedly stable below lambda in some sense. So the result that I mentioned here is exactly this result here. So this is a general result for AECs. So if an AEC has AP, JP, and non-maximal model, and there's some kappa such that if theta to the kappa equals theta, then K is theta stable, then you can show that if lambda to the kappa equals lambda, or for every mu less than lambda, mu to the kappa is less than lambda, then K has to have a universal model of size lambda. So the proof in this case, actually, if lambda to the kappa equals lambda, then you're lambda stable, and the result is due to Shelach. So you have a universal model. And if you have this other hypothesis, the idea is you're finally stable. And then by being finally stable and taking like unions of the universal models in the places where you're stable, then you can get a universal model in general. So these are the positive solutions. So these are sufficient conditions to have a universal model. So let's talk about negative results. So there's actually some negative results. So we have this result. If lambda is a regular cardinal, and there's mu an infinite cardinal, such that mu plus is less than lambda, and this is less than mu to the left 0, then the class of P groups doesn't have a universal model of size lambda. So this result, I mean, I wrote it down, but I would say it's due to Shelach and Kochman. And this result doesn't have to do anything with AECs. Actually, it has to do with combinatorial set theory and with club guessing sequences. So the result is completely different to what I've been saying. But with this result, together with the theorem from the last slide, we can get a very nice result for Fuchs' problem on below Aleph omega, with the exception of Aleph 0 and Aleph 1. And what one gets is that for n greater or equal to 2, P groups with pure embedding has a universal model of size Aleph n, if and only if 2 to the Aleph 0 is less or equal to Aleph n. So if 2 to the Aleph 0 is less or equal to Aleph n, then you use the theorem. And then if 2 to the Aleph 0 is greater than Aleph n, then you use this lemma here. And the reason you cannot use it for Aleph 1 is because if you take Aleph 1, you cannot find a mu that satisfies this part, because Aleph 1 is too small to have this. Aleph 0 doesn't work, and there's nothing below Aleph 0. So then I was, okay, what can we say about Aleph 1? So for Aleph 1, I have some partial solution. And the partial solution is that, okay, if 2 to the Aleph 0 is equal to Aleph 1, you have to have a universal model. And then if 2 to the Aleph 0 is greater than Aleph 1, and then you have to assume this combinatorial principle called club, then the class of P groups doesn't have a universal model in cardinality Aleph 1. One would like to say this seems to be like an extra hypothesis, but I don't know how to get rid of it. And for what I understand, if you want to use club guessing sequences, for sure you need this, but maybe there's a way of proving this theorem without using like Shalach's ideas. Okay, so now let's talk about some open problems. So actually, I haven't completely solved Fuchs' problem. So the first cardinal, it's Aleph 0, and it's still open. So does the class of P groups with pure embeddings have a universal model, a countable universal model? I have been working on this for a while, and every time I convince myself that the answer is yes, I found a reason why it's not. And every time I convince myself that it's false, I cannot prove it. So it's quite open. And then moreover, what happens with, for example, Aleph omega? So for Aleph omega, there's a partial solution. So if 2 to the Aleph 0 is less than Aleph omega, you have a universal model of cardinality Aleph omega. But if Aleph omega is less than 2 to the Aleph 0, no idea what happens. And more generally, the open problem is what happens with singular cardinals. So if you remember this lemma here, this lemma talks about regular cardinals. So what happens with singular cardinals is still wide open, I would say. So if you're more interested like in set theoretic algebra, these problems are more like have this like set theoretic algebra flavor more than this AC flavor. And finally, just to tell you something about torsion-free groups with pure embedding. So as I mentioned, Shalach has many results for this class, and he actually kind of solved the problem completely. He divides it, I think, in 6 cases, depending if the cardinal is singular, if the cofinality is countable, if it's uncountable, and like many other cases. And what I was able to do is like using this technique of first proving a stability and then proving that you have AP, JEP, and non-maximal models, I was able to extend all the positive results to any class of flat modules. So AECs help you, if you want to find universal models, AECs help you to get positive results. If you want negative results, then you probably need set theory. So set theory comes in. Okay, so this is all I want to, are there any questions about this? Okay, so this is all I want to say about universal models. So in the last, I guess like 5 to 10 minutes, how much time do I have? Like, yeah.
Yeah, 10 minutes is certainly fine.
Okay, so in the next 5 to 10 minutes, I'm gonna say something about superstability. So again, as I mentioned at some point, superstability was introduced by Shalach. Actually, for AECs, it was introduced in the 90s, but for a long time, it suffered from schizophrenia. So what do I mean by that? So there were many notions that for first order were equivalent, but for AECs, we didn't know if they were equivalent or not. But recently, Grossberg and Basie actually showed that all of these notions that we thought were equivalent, they're actually equivalent for AECs under AP, JEP, non-maximal models, and another hypothesis called tameness that I haven't introduced. And something else I want to say before introducing superstability is that if you have never seen superstability, superstability is a stronger property than stability. So if you're super stable, then you're stable. And we'll see this is true, but just to keep it in mind, like in the background. Okay, so before I introduce superstability, I have to introduce 2 notions. So first, I'm going to introduce the notion of universal extension. So M is universal in N if M and N have the same size. N is a K substructure of N. And the idea is for any N star in K of size M, if N is a K-substructure of n prime. The idea is you can map n star to m over n. So there's a map from n star that fixes n that goes into m. Okay, so this is actually a strengthening of being like a universal model in the sense of the previous section. Okay, and now with this, we're going to introduce the notion of limit model. And this notion is actually very important. It's a very important, like it's a very important notion to understand superstability, I would say. So what's a limit model? So let lambda be an infinite cardinal and alpha less than lambda plus be at limit ordinal. So M is a lambda alpha limit model over N if there is some sequence mi with I less than alpha containing k lambda, an increasing and continuous chain such that, okay, the first two properties are that M0 has to be N, which is this N here. Then the union of everything has to be M. And then the important property is that mi plus 1 is universal over mi for each I less than alpha. Okay, so this is the key property. Property 3 again is the key property. And so we say that M is a lambda limit model if there is an alpha less than lambda plus limit ordinal such that n in k lambda such that M is a lambda alpha limit model over M. So these are like a weakening of saturated models if you have seen them in first order. They're like a weakening of saturated models, but they are actually a very interesting object that for first order theories, like it hasn't been studied, but it could actually have some information also for first order theories. Okay, so first, when do they exist? So for K and AEC with AP, JP, and non-maximum model, K is lambda stable if and only if there is a lambda limit model. And what's the interesting question about limit models? So limit models, as you can see, so if you fix a cardinal lambda, what you're changing is this alpha. So you're looking at all the alpha limit ordinals below lambda. So the interesting question is, given a fixed cardinal lambda, how many lambda limit models there are? And more importantly, when do you only have one limit model? So this is what I introduced here. So K has uniqueness of limit models of cardinality lambda. If K has a lambda limit model, and you give any two lambda limit models, M and N are isomorphic. And with this notion, we can introduce the notion of superstability for AECs. So we say that K is superstable if and only if K has uniqueness of limit models in a tail of cardinals. What do I mean by this? I mean there's a cardinal mu, such that for every cardinal lambda greater than mu, K has uniqueness of limit models of cardinality lambda. Okay, so if you had seen superstability for first order, this looks like a very strange property, but this is actually equivalent to superstability for first order theories. First, it's clear that if you're superstable in this sense, then you have lambda limit models in a tail of cardinals. And since you have lambda limit models in a tail of cardinals, because of this result, you're lambda stable in a tail of cardinals. And this is the notion of superstability for first order theories. The other direction is harder. And then the other direction uses the fact that if you're superstable, then you know that kappa of t, which has to be LF0. So every model, every type doesn't fork over a finite set. And then using that, you can prove the equivalence. Well, I won't go over the details. So question 3, and I think I'm gonna finish basically with this, is if you have an AEC of modules, under what conditions is K superstable? So question 1 was, are all AECs are all AECs of modules stable? And then question 3 is, under what conditions is superstable? Even for first order, we know that not first order theories of modules are super stable. Some of them are stable, but not super stable. And more importantly I would say is, and the reason the question I think it's more interesting is there an algebraic reason why that happens? So, and we'll see that there's actually an algebraic reason why a class is stable. It's super stable and not only stable. And the key idea here is to characterize limit models algebraically. So these limit models, they look like a very strange thing, but if you want to understand superstability in AECs of module, you have to understand limit models, and you have to identify it with well-understood classes of modules. So what I want to say is, okay, I think I don't have that much time. So the result I want to mention 2 results. So first is this result here. So what I was able to do is find new characterization of Noetherian rings using this notion of superstability. So Noetherian rings are very well-known rings, and the characterization we care about is this one. Every absolutely pure module is injective. And what I was able to show is that a ring is left-Noetherian if and only if the class of absolutely pure modules with pure embeddings is superstable, if and only if the class of locally injective modules with pure embeddings is superstable. And then using like different results to what I have presented, one can actually obtain this other characterization, which is even more natural. That is that R is left-Noetherian if and only if the class of R modules with embeddings is superstable. And you can do a similar thing for pure semisimple rings. So pure semisimple rings, these are not as well known, I would say, but they were introduced in the 70s and they were studied a lot in the 70s and 80s. The definition is that every R module is pure injective, and the equivalence that I want to point out is this one here. So R is left pure semisimple if and only if the class of R modules with pure embeddings is superstable. So this is just a generalization of this result. What happens if you change embeddings? For pure embeddings, you go from left-Noetherian to pure semisimple. And another result is that if the class of locally pure injective module is superstable, then R is pure semisimple. And there are other results about perfect rings that I won't talk about. And yeah, I think I'll finish with this. And here are some references. The first section is based on this article. Then the second section is based on this article. And the last section, which I just rushed through it, is based on these two articles. And thank you very much.
Okay, thanks very much to Marcus for a nice talk. We usually have a silent round of applause.
Thanks.
And if anyone would like to ask a question, feel free to unmute yourself and ask a question.
I just had a question about that combinatorial principle that I think you call it CLAV, the one with the, yes?
Yes.
Can you say what it says, or?
I mean,
or where can I find it?
It's in Shala's book. Like, it's a weakening of diamond principle. So it's similar to diamond principle, but it's a weakening of it.
All right. Okay.
It basically tells you that you have club guessing sequences, whatever they are.
That you have, sorry, what?
Club guessing sequences. So if lambda is bigger than a left one, you can prove it in CFC. But if lambda is a left one, you need actually an extra principle. And that's what that principle tells you, basically.
Okay.
Any more questions or comments? Well, if not, then let's thank Marcus again for a very nice talk.
Thank you.
And that's it. So we can stop recording.